All right, let's go. So let's kick off the first video. 4.1, plate tectonics, living in California. You all know about earthquakes. I did not grow up here, and I have yet, since moving here in '98, I have not been in like a major earthquake, which I'm sure will change. And maybe you haven't either. The last major earthquake was the '94 Northridge earthquake, which was before your time, I'm pretty sure. We've had some smaller ones. There's a Whittier thing a couple of years ago, but you probably have not been in a situation where there's massive destruction and problems with transportation because of earthquakes. But I started out this little cartoon because it's just, I think it's really funny. I've always been really curious about the shape of South America and Africa because it looks like they fit together like puzzle pieces, yet they're, I think, about 2,000 miles apart. Well, why is that? Well, the answer is plate tectonics. They used to be connected. Oh, my little thing is failing. Okay, let's go. They used to be connected in one piece, Pangea, as you guys have heard of before. But because of seafloor spreading, there's a big crack that goes all down the Atlantic Ocean, pushing out from the middle. They've been moving apart for millions of years, about 1 centimeter every year. So I have this, well, we've been drifting apart during the last 50 million years. So we have enduring understandings we need to talk about for each topic, each subtopic and subtopic. And this one is, the Earth has all these systems that interact over time and balance each other out. And in this case, we have plates that are moving, and this creates tension. Tension/stress. And to release the stress, there needs to be, large movements, which are earthquakes. Relieve stress. You guys all want to relieve stress, right? And the reason the plates are moving is because the middle of the Earth is extremely hot, and magma rises, and that pushes plates around because the magma is coming up through the crust, creating new crust. We'll say due to, and we'll get to this later, magma rising from the mantle, which I think you've heard about, and that pushes plates around and makes plates move in all sorts of very interesting, complicated ways. And our learning objective for 4.1 is basically you need to know about convergent, divergent, and transform plate boundaries. This one right here is most important to us here in California, because you've all heard of the San Andreas Fault. You've probably seen the Rock movie, San Andreas. Woo! Maybe we could watch that in class. Good idea. I love the Rock. I think that was a solid Rock movie. Not one of my favorite Rock movies, but a solid one. But we have convergent and divergent boundaries happening all over the world, convergent coming together. This you'll see it's more so on the east coast of South America, west coast. West. As an example. And divergent coming apart, the mid-Atlantic ridge I just talked to you about. Just a couple examples there. There we go. Now let's get into the nitty gritty. Okay. Now, here we have this image is from the Northwest, which is where I'm from. I'm from a little city called Yakima that's over here. This is, Seattle. This is Oregon here, where you see Corvallis. But so actually, I would be more up in this direction, my little town. But here you have this subduction zone, this convergent boundary where you have the Juan de Fuca plate moving underneath the North American plate, and that's creating volcanoes, and therefore earthquakes happening along that North American plate. So let's kind of label it up a little bit. This is the Pacific plate, a huge plate. This area here, this is called a locked zone earthquake, where you have a lot of tension building. And right here, this is the Juan de Fuca plate is subducting. Let's see, Juan de Fuca. Subducting. Going underneath that North American plate, and you'll notice, since we're at the boundary, we have the ocean. Water gets under there, and it kind of helps to lubricate, actually, and create steam, and that creates heat and adds to the pressure that you'll see, rising up, from below to create these earthquakes. But you see, this is magma. Let me rewrite that a little better. Over time, you figure out what my letters mean. That's that molten rock rising up, creating the volcanoes, and then creating that pressure inside, which then lead to eruption. And these right here, these are the volcanoes in the Cascade Range. Volcanoes in the Cascades. Like Mount Rainier, Mount St. Helens. I got it right there. And I'll say St. Helens because that, along with Mount Lawson here in California, two the only volcanoes to erupt on the West Coast in the 20th century. So I was alive in 1980. 1980 when Mount St. Helens erupted. And in my town, which is, like I said, this way, east of Mount St. Helens, it went completely dark in the middle of the day. Lights went on. It was a trip. I remember it pretty clearly. But as a little kid, it was so fun to play with all that ash afterwards, kind of build with it, make little car tracks with it. Yeah, I thought it was kind of fun. My parents, all the adults, they got to deal with it. Not so much fun. But about 58 people were killed in that eruption. Most of them were near the mountain when it blew, and they just didn't get out of the way, or they knew it was there, but they were just curious, right? You know how people are. So yeah, that shows what's going on in the Northwest with our plates. Just some more description of that. This is volcanic arc islands we see in the Pacific, like the Aleutian Islands in Japan. So you guys are all familiar with Japan, right? You might not know the Aleutian Islands up in Alaska. It's very similar. It's all a volcanic island arc that we see from these subduction zones. There's something called an accretionary wedge. That's a fancy word for basically just kind of like garbage rocks, right? Just all all sorts of rocks just been kind of sitting around on that plate, just over time, just kind of getting jammed together and just kind of. It's called accretionary, and the coastal mountains here, a lot of these rocks are accretionary too. We'll get to that next slide. But we see here, again, this plate going underneath another. This would be the lithosphere, and you see that it's supposed to be covered up. On yours, it's covered up with asthenosphere, so I don't have to write it, but it's already there. And as the lithosphere, basically, that's also called the crust. As it goes under, this is where you're going to have earthquakes. These little POW symbols, those are symbolizing earthquakes. Earthquakes, yeah. And again, you see magma rising up here. Lower right of my screen is blocked off because of my the filming video box, but I can see it. That's the magma rising up from all that heat and friction that's being created when those two plates rub each other like that. All right, now this is what we're talking about with California. All right, I mentioned before the accretionary wedge, all this kind of leftover stuff, uplifted ocean sediments, other sorts of little islands, little volcanoes that were stuck on that plate from before. They all just kind of get pushed together as this is about actually from this, showing California about 30 million years ago. This would be the Farallon plate, which doesn't exist anymore. It now is completely gone underneath North American plate there. But before it did, it left a lot of stuff behind. The coastal range. I like to ride my bike from here on up to Santa Monica and those mountains above Santa Monica, and basically I think it's called the Malibu State Park. Anyway, all those hills up there, basically uplifted ocean sediments, 20-30 million years old. And that forms a coastal range, which we have all along the coast here, pretty much from San Diego and below on up to San Francisco. Then we have the Great Basin, okay, where all the agriculture of California is grown. You might note also Great Valley. And then right here, Sierra Nevada mountains. Which you'll see volcanoes. You go to Sierra Nevadas today. You don't see volcanoes except for Mount Lawson. I'll show you in a second. But most of the Sierra Nevadas, they're not volcanic. It's basically a big chunk of molten magma came up and got stuck and just formed this huge big piece of granite under the surface, and then over time got weathered away, and that's what you see now is just all this magma that just kind of got stuck. It's called a pluton, basically. And remember, Pluto is the Greek god of the underworld, I think. Stuff's coming from underneath. But all these mountains are also called a batholith. But basically, a mountain that kind of gets, like a big volcano, gets stuck underground. And then over time, like I said, it weathered away, and then you see what we have now. I think I mentioned before, granite is that volcanic rock that's very dominant in what you see. Half Dome, the west, the Dawn Wall. There have been a lot of movies out lately about people climbing those. Maybe you're familiar. So what I want you to do next is I want you, this is where you get in there. Draw and label a convergent boundary. So you can use these as a guide. I want you to draw a good one, label it. I'll be scoring you based on, how much time I see you, working on it and labeling it. So pause and do that, and then come back here, or go back and do it later, however you're most comfortable. But what I did is all the way from Washington down to northern California, you have volcanic peaks. And this is where the last volcanic peak is on the west coast. Everything south of here, all of this, the main Sierras, this is not volcanic. There are some, it's very interesting. Scientists have a hard time explaining it. There are some hot springs near, let's see, it's not really on here, down. Yeah, near Death Valley, very kind of, maybe you can see it. There are some hot springs which point to some magma, but scientists are really unclear where it's coming from or how it got there. There's theories and ideas, of course, but the main thing, this is the last volcanic peak in that Cascade Mountain range, and this is when in 1915, again, this is Mount Lawson. Pretty cool, huh? In that 1915, somebody having a camera was not common. They must have known something was going to go on, I bet, though. Somebody wanted to set up a camera and try this. Like, check out my new camera. And just got an amazing shot right there. It looked like it's kind of coming towards where the camera person is. It must have been okay. This whole thing would be, whole camera would be obliterated. And here you can see Mount Lawson today. Beautiful. And I'm not sure if there are earthquakes or anything happening there now. Mount Rainier in Washington State does from time to time have earthquakes, I believe. Scientists think it could become active again. And Mount St. Helens could become active again. This is hard. Predicting earthquakes and volcanoes is difficult. It's still something scientists are really trying to get a grip on. But they are pretty good at knowing if it's about to blow in the next month or year. Usually they're pretty accurate. Here's a cool, I just want to show an example of island arc. I found this one. This island is called Aogashima. And it's in Japan. It's about 60 miles south of Tokyo. Not easy to get to. But it looks so amazing. Man, that should be in a movie. Check it out. It's got a volcano within a volcano. That's just awesome. I wonder if there's a volcano in that. I wonder if there's a big volcano underneath this thing. But anyway, I just wanted to show you that. Really cool. Aogashima, Japan. All right. So make sure you fill out your slide packet with all the interactives, and then add whatever I asked you to add on Canvas, either probably a thinking map or a list of questions and answers.